Section 2.3, our objective is I can use the midpoint theorem and the angle bisector theorem. Okay, now let's start looking at a segment. So if you have segment AB and M is the midpoint, so M is the midpoint of segment AB. Then by definition of midpoint, we can conclude we can say that length of AM equals length of MB. Okay, so midpoint tells us that we have two equal lengths. Now, if length of AB equals 6, then it's true that length of AM equals length of MB equals 1/2 of length AB. So each one of those is half of the whole. And that is essentially what the midpoint theorem says. It's the midpoint theorem says this. If M is the midpoint of any segment AB, then the length of AM is equal to 1/2 the length of AB, and the length of MB is equal to 1/2 the length of AB. Now be very careful not to confuse the definition of midpoint from the midpoint theorem. The definition of midpoint says you have two equal pieces. Okay? The midpoint theorem says that each piece is half of the whole. So if you are saying that two pieces are equal, two pieces of the segment are equal, then you're going to use the definition of midpoint. If you're saying that one of the pieces is half of the whole segment, then you're going to use the midpoint theorem. So the midpoint theorem has to have the idea of half in it. So here's an example. So let's say I have this picture where this is P, this is S, this is Q, and I have segment PQ. Okay? And I'm given R is, oops, it should be R. And I wrote B, it should be R. Okay? R is the midpoint of segment SQ. Okay? Then, what allows me to say that segment SR is congruent to segment RQ? Okay? Well, let's look at this. Segment SR is this one. Segment QR is that one. And I know R is the midpoint. So I'm saying two pieces are equal. So the thing that allows me to say that is the midpoint definition. Oops. Definition of midpoint. That's what allows me to say that those two are equal. What allows me to say that length of SR equals 1/2 the length of SQ? Well, notice that SQ is the whole segment, and I'm saying that SR is half of the whole. So that is an application of the midpoint theorem. Okay? What allows me to say that length of SR plus length of RQ equals length of SQ? So I'm taking this plus this equals the whole thing. And that is an application of the segment addition postulate. And finally, what allows me to say that segment PR bisects segment SQ? Okay, well, PR is a segment, and it's a segment that goes through the midpoint of SQ. So that's the definition of a segment bisector. Okay. All right, let's look at another example. Right, I have this diagram. This is H, L, K, and J. And I have JL and I have KH, and they intersect at point X. Okay? And I'm given that segment HK bisects segment JL. I'm given X is the midpoint of segment HK. And what justifies me being able to say the following statements? So first of all, HK, which is this one, bisects JL. So the fact that it's bisecting, by definition, tells me that HK goes through the center of JL. So that means this is congruent to this. Okay? And also, if X is the midpoint of HK, that means that this is congruent to this. Okay? So, what allows me to say that HX is equal to XK? Okay? Well, that's definition of midpoint. Okay? From right there. Okay? Then what allows me to say that HX is equal to 1/2 HK? Okay? Well, HX is this. HK is the whole, and I'm saying it's half, so that's the midpoint theorem. Allows me to say that. What allows me to say that X is the midpoint of segment JL? Well, that is definition of segment bisector, because here I'm told that it bisects. The bisector goes through the center, so if it goes through the center, by definition it has to be the midpoint, right? And then 4, what allows me to say that length of JL is equal to length of JX plus length of XL? So this whole thing is equal to this plus this, and that is an application of the segment addition postulate. Okay, now let's go on to our second theorem. Okay, So if I have an angle A, B, C, and I have ray BX, okay? And if I'm told that ray BX bisects angle ABC, then by definition of an angle bisector, that means that measure of angle ABX has to equal measure of angle XBC by definition of angle bisector. So this measure equals this measure, okay? So if we are told that a measure of angle ABC equals 60 degrees, then just like with the segment, the midpoint theorem, we can say, we can say then that measure of angle ABX equals measure of angle XBC, that should be a C, equals 1/2 measure of angle ABC. Because if this whole thing is 60 degrees, then, and ray BX divides it exactly in half, this one has to be 30, and this one has to be 30. Okay? So that's 1/2 of 60, or 30 degrees. And that essentially is the angle bisector theorem. Which says exactly this. If ray BX is the bisector of angle ABC, and let me put the picture down here again so we can see it. Then measure of angle ABX equals 1/2 measure of angle ABC, and measure of angle XBC equals 1/2 measure of angle ABC. Okay? So let's look at an example again. So let's say that I have this picture. So this is F, this is C, this is D, and this is E. Okay? And given that ray FD bisects angle CFE, what allows me to say that measure of angle CFD is equal to 1/2 measure of angle CFE? Okay? Well, here we're saying that an angle is half of the whole, so that's an application of the angle bisector theorem. Okay? B, what allows me to say that measure of angle CFD equals measure of angle DFE? Okay? Well, here I'm saying that these two are the same size because I know that this is a bisector of the angle, and so that's definition of angle bisector. Okay, so again, notice If I'm saying two pieces are equal, it's definition. If I'm saying a piece is half of the whole, it's the theorem. And what allows me to say that that length of CD plus length of DE equals length of CE. So this plus this equals the whole. Okay, what am I doing? I'm adding segments to equal the whole segment, and so that is segment addition postulate. Okay. All right, so let's look at an actual proof. Okay, so given that M is the midpoint of segment PQ and N is the midpoint of segment RS, and that length of PQ equals length of RS. Prove that length of PM equals length of RN. Okay, and here's the picture. Here's P, Q, and there's M, and I have another segment R, S, and there's N. Notice that nothing I wrote down in the given or the prove made any sense at all until I provided a picture for you. Okay, now it kind of makes sense. So now we're ready to do our actual proof. So this is called a two-column proof. We have our statements on one side and the reasons on the other side. Okay, so number one, I'm going to use these first two parts. M is the midpoint of P segment PQ, and N is the midpoint of segment RS. And I can say that because it's given. Okay, so if M is the midpoint of this, then that is essentially telling me that length of PM equals length of MQ. Okay? And if N is the midpoint of RS, then that is telling me that length of RN equals length of NS. Okay? So I got that from the definition of midpoint. Okay? And it is also true that PM is half of PQ. So I can say, number two, length of PM is equal to 1/2 PQ. And it's also true that length of RN is equal to 1/2 the length of RS. So what did I apply there? Okay, what theorem, postulate, or definition did I apply? Well, this is the midpoint theorem. Because notice it's talking about a piece being half of the whole. Then I'm going to use the second part of my given, that length of PQ equals length of RS. That was given to us again in the given statements. Okay? Then now using these two lines, actually, I'm going to use this line. and I'm going to multiply through by 1/2. So 1/2 PQ equals 1/2 RS. And that is just the multiplication property. Okay? Now, using this line 2 and line 4, because 1/2 PQ equals PM, I can replace this with PM. And the same thing here, 1/2 RS equals RN, so I can replace length of RN, and so what I used was substitution. And now, notice that my last line in my statements matches exactly what I was trying to prove, so I am done.